You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Drift and degradation are terms used to describe the gradual decline of artificial intelligence model performance when exposed to the dynamic conditions of the real world. Even the most sophisticated models, once deployed, inevitably face environments that differ from the carefully curated data they were trained on. Users change their behavior, industries adopt new terminology, markets evolve, and external events reshape the context in which predictions are made. Drift refers to these changes in the data or environment, while degradation describes the resulting drop in accuracy, relevance, or reliability over time. Together, they represent one of the most significant challenges for sustaining AI at scale. Unlike initial training or deployment, which are discrete events, drift and degradation are continuous forces that demand ongoing attention. Effective organizations treat them not as rare anomalies but as inevitable phenomena, designing detection and refresh strategies to minimize harm and preserve trust. Drift can be defined as the situation in which the distribution of input data no longer matches the conditions under which a model was trained. A model might have been optimized for patterns that were stable at the time, but when inputs shift, those assumptions no longer hold. For example, a fraud detection system trained on last year's transaction patterns may misclassify new payment methods or unfamiliar merchant behaviors. The mismatch does not mean the model is poorly designed. It means the environment has changed. Drift is a reminder that machine learning is context-bound, and when context evolves, models must evolve with it. Identifying drift early is critical, because uncorrected drift leads directly to degradation in model effectiveness and user trust. Degradation is the observable decline in a system's ability to deliver accurate or reliable outputs as drift accumulates or as systems age. Where drift focuses on the change in input conditions, degradation is the manifestation of those changes in performance metrics. A recommendation engine might begin suggesting irrelevant items. A translation model might increasingly misinterpret idioms. Or a medical classifier might fail to recognize emerging symptoms of new conditions. Degradation can also result from technical factors such as hardware wear, scaling inefficiencies, or software updates that inadvertently alter model behavior. The key point is that degradation is not a question of if but when. Every deployed model will degrade eventually, and organizations must be prepared to detect and address it proactively. The causes of drift are varied and often subtle. Seasonal trends, for instance, can shift purchasing behaviors in e-commerce, confusing recommendation engines that were trained on off-season data. New slang or cultural references may appear in customer interactions, throwing off natural language models that have not seen these terms before. Regulatory updates may change the rules governing financial transactions or medical reporting, requiring models to adapt to new compliance structures. Even global events like pandemics can create sudden, dramatic changes in data distributions, rendering past assumptions obsolete. Recognizing these causes is the first step toward building resilient systems. Drift is not random. It follows patterns driven by human behavior, technological innovation, and external forces. Understanding these drivers enables better monitoring and quicker response. A useful distinction exists between concept drift and data drift. Concept drift occurs when the relationships between inputs and outputs change, such as when the definition of fraudulent activity evolves with new payment technologies. Data drift, by contrast, refers to changes in the distribution of input variables themselves, even if the relationships remain stable. For example, the demographic composition of a user base may shift over time, altering the balance of data presented to a model. Both forms of drift undermine performance but require different strategies to address. Concept drift often calls for updates in model reasoning or feature design, while data drift may be handled through rebalancing or retraining with new samples. By distinguishing between the two, Organizations can triage more effectively and avoid one-size-fits-all remedies that fail to address root causes. Real-world examples illustrate how quickly drift can appear and affect performance. Fraud detection systems are especially vulnerable, as adversaries constantly adapt their strategies to evade detection. A model that worked well last month may already be outdated this month as criminals exploit new payment methods or transaction patterns. Customer service bots also face rapid drift when users adopt new slang, memes, or cultural references that were absent from training data. Even search engines encounter drift when trending topics change the meaning of common queries. In each case, the pace of drift can outstrip expectations, and organizations that fail to monitor continuously find themselves lagging behind user needs. These examples highlight why drift is not a hypothetical problem but an operational reality that demands vigilance. Triage is the process of prioritizing which drift issues require urgent response and which can be monitored over time. Not every instance of drift leads to catastrophic degradation. Some shifts may be minor and tolerable, while others pose immediate risks. For example, a chatbot that fails to understand a new meme may cause mild annoyance, whereas a medical diagnostic system that misclassifies emerging conditions could cause serious harm. Effective triage involves assessing impact, risk, and urgency. This requires not only automated detection but also human judgment, since domain experts can contextualize whether a drift signal is critical or manageable. Triage ensures that limited resources are directed where they matter most, preventing organizations from overreacting to noise while missing genuine threats to performance and safety. Detection methods for drift combine statistical monitoring, accuracy tracking, and user feedback. One approach is to monitor the distribution of incoming data and compare it to training distributions, flagging significant deviations. Another is to track performance metrics like accuracy, recall, or F1 score over time, watching for declines. User feedback, such as ratings or complaints, also provides valuable signals of degradation. More advanced methods involve anomaly detection, where machine learning models identify unusual patterns in inputs or outputs that may indicate drift. Combining these techniques increases reliability, since no single method is sufficient alone. Detection must also balance sensitivity with specificity, avoiding constant false alarms while catching genuine drift early. The goal is to create monitoring systems that act as sentinels, alerting organizations before problems affect users. Evaluation metrics used in drift detection vary depending on the domain but share common principles. Statistical distance measures, such as Kullback-Leibler divergence, quantify how far new data distributions deviate from training sets. Accuracy decay tracks the decline in traditional performance metrics, providing direct evidence of degradation. Anomaly detection methods highlight sudden or unusual shifts in behavior. Some organizations use composite scores that combine multiple signals into a single index of drift risk. Metrics must be tailored to the application, since what constitutes drift in fraud detection may differ from drift in natural language processing. The diversity of metrics underscores that drift is not a single phenomenon, but a collection of challenges requiring domain-specific tools for measurement and response. The latency of detection plays a critical role in determining the impact of drift. Slow detection allows errors to propagate, frustrating users, harming trust, or even causing financial or safety risks. For example, a healthcare system that fails to detect drift in diagnostic models may continue producing incorrect assessments until retraining occurs, potentially affecting thousands of patients. Faster detection minimizes damage by allowing organizations to intervene before degradation spreads widely. This requires near real-time monitoring in some contexts, supported by efficient data pipelines and alerting systems. While instant detection is not always possible, reducing latency wherever feasible improves resilience. Organizations must design their monitoring not only to catch drift, but to catch it quickly enough to matter. The impact of degradation, if left unaddressed, can extend beyond technical performance to affect organizational trust, compliance, and safety. Users who encounter irrelevant recommendations or unhelpful chatbot responses may disengage, reducing adoption and satisfaction. In regulated industries, degraded models may produce outputs that violate compliance standards, exposing organizations to penalties. In safety-critical domains like medicine or autonomous driving, degradation may lead directly to harm. These consequences highlight why degradation is not a minor inconvenience, but a serious operational risk. The reputational damage from failing to address degradation often exceeds the technical challenges of retraining. Organizations that treat drift and degradation as strategic concerns, not just technical issues, are better positioned to maintain trust and resilience. Cadence of model refresh refers to the rhythm at which models are updated to counteract, drift, and restore performance. Some domains require frequent refreshes, such as fraud detection, where adversaries adapt constantly. Others can refresh less often, depending on the stability of their environments. Establishing the right cadence requires balancing cost and risk. Frequent updates improve accuracy but increase expenses, while infrequent updates save resources but allow more degradation. Organizations must find the cadence that aligns with their domain's dynamics, user expectations, and regulatory requirements. Refresh cadence is not static. It must evolve as contexts change. Building refresh cycles into operational planning ensures that drift management is proactive rather than reactive. Monitoring can occur both online, in real time, and offline, through batch analysis of accumulated data. Online monitoring captures drift as it happens, supporting rapid intervention in critical domains. Offline monitoring provides more thorough analysis, allowing for detailed comparisons of distributions and performance trends. Both approaches are complementary. Online monitoring provides agility, while offline monitoring provides depth. For example, a bank might use online monitoring to detect sudden anomalies in transactions, while running offline analyses to study long-term shifts in user behavior. By combining these approaches, organizations achieve both speed and thoroughness, ensuring that drift is detected accurately and addressed effectively. Human oversight remains essential in drift detection and management. While automated systems provide alerts and metrics, domain experts provide the context needed to interpret them. A statistical signal may suggest drift, but only experts can determine whether it reflects meaningful change or harmless variation. For example, clinicians may judge whether a drift signal in diagnostic models reflects new disease trends or merely seasonal fluctuations. Legal experts may decide whether changes in case law require retraining. Human oversight ensures that responses are not blindly automated but guided by professional judgment. This combination of machine detection and human interpretation creates a balanced approach, ensuring that organizations respond effectively to drift without overreacting to noise. Enterprise implications of drift and degradation are significant as they touch on compliance, safety, and customer trust. Organizations that fail to manage drift risk legal penalties, reputational damage, and loss of user confidence. Regulators increasingly expect companies to demonstrate active monitoring and retraining as part of responsible AI governance. Customers also expect consistent performance. Encountering degradation erodes trust quickly. Enterprises must therefore build drift management into their operational strategies, treating it as a core part of lifecycle management rather than an afterthought. By doing so, they create systems that are not only technically resilient, but also aligned with the demands of compliance, accountability, and long-term trustworthiness. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Adaptive models represent one of the most proactive strategies for combating drift, since they incorporate mechanisms to learn continuously from new data rather than waiting for periodic retraining cycles. Instead of freezing a model at deployment, adaptive systems update parameters incrementally as they encounter new inputs, ensuring that patterns reflect current conditions. This is particularly valuable in domains like fraud detection or social media moderation, where new behaviors emerge rapidly and static models quickly lose effectiveness. However, adaptive systems also carry risks. Continuous updates may incorporate spurious or adversarial patterns if safeguards are not in place. Without careful oversight, an adaptive model might learn incorrect correlations from noisy or biased inputs. Thus, adaptive learning requires strong monitoring, quality filters, and human checkpoints to ensure that updates genuinely improve performance. When designed responsibly, adaptive models offer organizations the agility to stay aligned with fast-changing environments while reducing the lag associated with traditional retraining schedules. Retraining triggers are the rules or thresholds that determine when a model must be refreshed. Instead of updating continuously, most organizations set criteria to decide when drift has reached a point that threatens performance or compliance. These triggers might include specific accuracy declines, shifts in input data distributions, or increases in user complaints. For example, if accuracy drops below 90% on a golden dataset, retraining may be initiated automatically. Triggers can also be tied to external events, such as regulatory changes that mandate updates to ensure compliance. The design of retraining triggers is critical, since setting thresholds too high risks prolonged degradation, while setting them too low leads to costly over-retraining. Effective organizations calibrate these triggers through experimentation and monitoring, ensuring that retraining is timely without being wasteful. Retraining triggers act as the guardrails of drift management, balancing the need for responsiveness with the realities of operational cost. Rolling refresh strategies offer a way to manage retraining without disrupting service or exposing users to untested models. Instead of replacing a model all at once, updates are rolled out gradually across different user segments or geographic regions. This staggered approach allows organizations to test retrained versions in production conditions while keeping the majority of users on stable versions. If issues arise, rollouts can be paused or adjusted before full deployment. For example, an e-commerce platform might refresh its recommendation engine in phases, starting with a small percentage of traffic before expanding to all users. Rolling strategies reduce risk, improve resilience, and provide more opportunities for monitoring real-world performance during the transition. They represent a pragmatic approach to drift management, recognizing that deployment is as much about managing uncertainty as it is about updating accuracy. Model versioning is essential for managing drift, as it allows organizations to track, compare, and roll back models when necessary. Every retrained or adapted model should be treated as a distinct version, complete with metadata about training data, configuration, and performance benchmarks. Versioning ensures transparency, enabling teams to understand how and why changes occurred. It also supports rollback, providing a safety net if a retrained model performs worse than its predecessor. For example, a healthcare organization deploying diagnostic models must maintain strict version control to comply with regulatory requirements and preserve audit trails. Versioning also aids collaboration since teams can reference specific versions when discussing results or debugging. Without versioning, drift management becomes chaotic, with no clear record of how models evolve over time. With versioning, drift management becomes disciplined, accountable, and auditable. Evaluating retrained models is critical to ensure that updates truly restore or improve performance. Before replacing a prior version, retrained models are tested side by side against golden datasets, benchmarks, or even live traffic in controlled experiments. These comparisons reveal whether retraining has corrected drift-related degradation or inadvertently introduced new errors. Evaluation also includes domain-specific criteria, such as compliance in finance or clinical accuracy in healthcare. For example, a retrained fraud detection model might be tested on both historical fraud cases and new attack patterns to confirm coverage. Without rigorous evaluation, organizations risk adopting retrained models that solve one problem but create others. By institutionalizing side-by-side evaluation, teams maintain confidence that retraining delivers genuine improvements while safeguarding against regressions. Synthetic data use has emerged as a valuable tool for combating drift, especially when real-world data is scarce, restricted, or slow to accumulate. Synthetic data can be generated to simulate new patterns or augment underrepresented cases, providing additional coverage for retraining. For instance, fraud detection teams might simulate novel transaction scenarios to train models against emerging threats, or legal AI developers might generate synthetic contracts to expand clause coverage. Synthetic data allows organizations to prepare for anticipated shifts proactively, reducing lag in adaptation. However, synthetic augmentation must be carefully validated since poorly generated data can mislead models. When combined with real data and expert oversight, synthetic data offers a scalable way to enhance resilience, ensuring that retraining reflects both current and potential future conditions. Benchmarking against drift represents another proactive approach, where evaluation frameworks simulate drift scenarios to test model resilience. Instead of waiting for drift to occur naturally, models are challenged with datasets that mimic possible shifts, such as new user demographics, language variations, or adversarial patterns. These simulated tests reveal weaknesses early, allowing organizations to design mitigation strategies in advance. For example, a customer service chatbot might be benchmarked against slang-heavy inputs or unusual question types to assess robustness. Benchmarks also allow organizations to compare resilience across models, informing strategic decisions about which systems to deploy in volatile environments. Benchmarking against drift turns drift management from a reactive process into a forward-looking practice, preparing models for the inevitable changes they will face. The cost of refreshing models is one of the most challenging aspects of drift management. Retraining requires compute resources, data engineering, validation, and deployment infrastructure, all of which add to operational expenses. Frequent refreshes can strain budgets, especially in industries where margins are tight. Organizations must therefore weigh the cost of retraining against the cost of degradation. In high-stakes domains like healthcare or finance, the cost of failure often exceeds the cost of retraining, justifying frequent updates. In consumer applications, organizations may accept more degradation to conserve resources. Cost considerations encourage innovation and efficiency, such as parameter-efficient retraining, incremental updates, or synthetic data augmentation. Managing cost effectively ensures that drift detection and refresh cadences remain sustainable over time. Automation in drift detection has become increasingly common, with organizations deploying anomaly detection frameworks and alerting systems to monitor inputs and outputs in real time. Automated tools can flag when data distributions shift, when accuracy declines, or when unusual behaviors appear. These alerts trigger further investigation or even automatic retraining pipelines in advanced systems. Automation ensures scale, making it possible to monitor thousands of models simultaneously without requiring human review of every signal. However, automation is only as effective as its design. Poorly calibrated alerts can overwhelm teams with false positives or miss subtle but critical shifts. The strength of automation lies in its ability to act as a first line of defense, catching potential drift quickly and consistently before humans step in for contextual interpretation. Despite its promise, automation has limitations, particularly in complex or sensitive domains. Automated systems may misinterpret harmless fluctuations as drift, generating unnecessary noise. They may also overlook deeper conceptual shifts that require domain expertise to recognize. For example, an automated detector might flag changes in transaction volumes without realizing that the definition of fraudulent activity has shifted due to new regulations. In such cases, human experts are indispensable for providing context and judgment. The limitations of automation highlight the importance of combining machine efficiency with human oversight. Effective drift management acknowledges that automation can scale monitoring but cannot replace expert review in interpreting the meaning and implications of detected drift. Drift also has security implications since malicious actors can exploit it to degrade models intentionally. By injecting adversarial inputs or manipulating data streams, attackers can create drift-like patterns that mislead models or erode performance. For example, fraudsters may deliberately exploit weaknesses in fraud detection systems by gradually shifting their behavior, making it harder for models to adapt. Drift detection frameworks must therefore account for adversarial risks, incorporating security monitoring alongside statistical checks. Security-conscious organizations recognize that drift is not always natural, but may be weaponized. Addressing this requires not only retraining pipelines but also defensive strategies to detect and counter malicious drift. This intersection of drift and security underscores the broader challenges of maintaining AI in adversarial environments. Ethical considerations arise because drift, if left unaddressed, often harms underserved groups disproportionately. Models trained on historical data may degrade more quickly for minority populations when conditions change, compounding inequities. For example, language models may fail to adapt to emerging dialects or slang used by marginalized communities, reducing inclusivity. In healthcare, models may degrade faster for populations underrepresented in training data, leading to unequal treatment. Ethical drift management requires monitoring impacts across demographics, ensuring that performance remains equitable as data shifts. By embedding fairness into drift detection and refresh processes, organizations ensure that adaptation does not reinforce systemic biases, but instead upholds commitments to inclusivity and justice. Cross-domain challenges highlight that drift manifests differently across industries, demanding tailored approaches. In finance, drift often appears as adversarial adaptations, where fraudsters actively evolve to bypass detection. In healthcare, drift may arise from changing medical guidelines, new diseases, or shifting patient demographics. In consumer AI, drift can be driven by cultural trends, evolving slang, or new user expectations. Each domain requires different detection methods, refresh cadences, and oversight mechanisms. Understanding these differences prevents organizations from applying generic solutions that fail to capture industry-specific risks. Cross-domain drift management emphasizes the need for domain expertise, contextual knowledge, and adaptive strategies that align with the unique dynamics of each field. The future outlook for drift detection and refresh pipelines is that they will become standard enterprise practices, integrated into AI lifecycle management. Just as monitoring and logging are now expected in software engineering, drift detection and retraining will become default components of AI deployment. Advances in adaptive learning, automation, and benchmarking will make pipelines more efficient and resilient, while regulatory pressures will formalize requirements for ongoing monitoring. Organizations that treat drift as an operational inevitability, not an occasional anomaly, will gain resilience and trust. Drift management will no longer be a reactive scramble, but a disciplined, proactive process embedded into workflows. By institutionalizing drift detection and refresh cadences, enterprises ensure that their AI systems remain accurate, safe, and trustworthy in the face of inevitable change. As organizations refine drift management, they naturally transition toward performance engineering, which focuses not only on maintaining accuracy but also on optimizing efficiency and scalability. Drift detection and refresh pipelines provide the stability necessary to ensure that models remain functional, while performance engineering ensures they remain cost-effective, fast, and robust under pressure. This progression highlights the interconnected nature of AI lifecycle practices, where drift management lays the groundwork for continuous optimization. By linking detection, triage, refresh, and performance engineering, organizations create systems that are not only resilient, but also sustainable and efficient over the long term. Drift and degradation, then, represent unavoidable realities of AI deployment, but they need not be destabilizing. With robust detection, careful triage, and disciplined refresh cadences, organizations can manage these challenges proactively. Adaptive models, retraining triggers, rolling strategies, and human oversight provide a toolkit for sustaining performance. Ethical and security considerations ensure that drift management does not merely preserve accuracy, but also protects fairness and resilience. By treating drift not as a flaw but as an expected dynamic, organizations shift from reactive firefighting to proactive stewardship. In doing so, they build systems that evolve with their environments, maintaining accuracy, compliance, and trust, even as the world around them changes. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.